Okay, so today we're going to be looking at rational expressions. Most importantly, our goal is to simplify the rational expressions. We're going to cover adding and subtracting rational expressions as well as finding partial fractions. So let's have a look at our starting activity. Here we're asked to simplify and identify any excluded values. So in order to identify excluded values, we have to start by factoring. So our first step for this one is to factor it. Factor the numerator, factor the denominator. So we can see we've got a perfect square there in the numerator. That's going to factor to x plus 3 squared. And then in the denominator we can factor this with two brackets. We've got x plus 3, x minus 5. So at this point we can identify any excluded values. An excluded value is a value which isn't in the domain if we were to sketch this function. We can see this by any value that will make the denominator 0. So what values are going to make the denominator 0? So x is not equal to 5. This is an excluded value. We cannot put this value into this function. It's not possible. X is not equal to negative 3. These are the excluded values. So looking at this function, is it going to have any vertical asymptotes? Just to connect to the last class that we looked, can we see any vertical asymptotes in this? We're going to have one vertical asymptote. What will it be? So we have a vertical asymptote. This isn't part of the question, but just to connect to the last class. What would the vertical asymptote be? 5 isn't an asymptote. X equals 5 is an asymptote. So this is going to be a vertical asymptote. What about the x equals negative 3? What will that create?
A hole.
That will create a hole. Why will it create a hole and not a vertical asymptote?
Because it's under. Because they cancel out.
Is it because it's negative?
No, because they cancel out.
Because there's two. Like one of them, they cancel out.
We have, it's not just because there's the same factor in the numerator as in the denominator, it's that the multiplicity of the factor in the numerator is greater than the multiplicity of the factor in the denominator. Okay? So this is going to give us a whole at x equals negative 3. We can simplify this expression further by cancelling our factors. We can cancel this factor x plus 3 with one of those factors in the numerator. So this expression is going to be equal to x plus 3 over x minus 5. Now this expression is only valid now with these constraints. Notice that x minus 3 remains an excluded value. X minus 3 remains an excluded value even though it doesn't now cause a divide by 0. This expression has to be the same as this expression. So in order to make it the same, we can add this hole in by just excluding it from the domain of the expression.
I have a question from the last class. You remember when you were saying that it's really hard to see the hole, like on the calculator?
You can't see the hole on the
So
calculator.
how would we draw it, or would we just say?
If you sketch it with an open circle. So this function we could sketch. If we were to graph this expression as a function, we would start by putting in our vertical asymptote at x equal to 5. We're going to put in our hole over here, like this. We can put in our horizontal asymptote. It's going to be here at y equal to 1. So then we can see that we've got to go through here and here. We're going to sketch. It's going to look like this. On this one, I probably sketched it fairly quickly, but let me just explain how I knew this. The vertical asymptote, x equal to 5, we can see here in the denominator. The whole at x equal to 3, we can see the fact that we have the same multiplicity in the numerator bigger than the denominator, but I also know because when it cancels down to that, that means that is going to be a 0. That whole will be at the 0. So I knew it was going to appear on the x-axis. I didn't have to calculate the y value because I saw that there was a factor remaining once I removed the whole, making that a 0 for the function without the whole, which let me very quickly sketch it. The horizontal asymptote I can see because the horizontal asymptote is equal to the quotient of the lead coefficients. The horizontal asymptote is equal to the quotient of the lead coefficients. In fact, if we get into slant asymptotes, you can see the slope of a slant asymptote by taking the quotient of the lead coefficients. It won't give you the equation, but it will give you the slope of the slant asymptote.
This is kind of off topic, but with the
So was that.
yeah, but with the rational function like have like an imaginary axis as well, like it can be imaginary roots too.
No. When we're sketching a function, we're only sketching it in the Cartesian coordinates, which are real. We don't sketch imaginary ones. Alright. So next up, we're looking at simplifying and identifying excluded values. So
First we factor.
let's
First
have,
you subtract.
let's have first you factor, and then you make the subtraction. Let's have you have a go at it for 2-3 minutes.
First you factor this. Factor, you don't factor those.
Okay, so here on this one, we're asked to simplify and identify excluded values. So first thing we need to do is decide on a common denominator. So in order to decide on a common denominator, you start off by factoring. You're going to have x squared minus 1 over x bracket x plus 3. So we can look and see what the factors are going to be. So this first one, we need to multiply top and bottom by x plus 3. So this first one, we need to multiply top and bottom by x plus 3. The second one, we need to multiply top and bottom by x.
Yeah. No, I knew it now. I knew
Oh,
it.
I didn't know you can do it.
Why X? Because now we're
You said so.
Oh, that's good.
Wait, you just multiplied by it.
You
So
just
the
multiply
lines
by
I
it.
get 3 over.
Because we had the number
Yeah,
of the
It's
cosine.
not usually
Not possible.
Sorry, if we just look,
It's just the
if we have an expression like this one, what's it equal to?
3.
We can multiply top and bottom by any number or by any letter. What's this equal to? Oh, sorry.
3.
We don't change the number. We multiply top and bottom by any number. So in this case, I'm multiplying the top and bottom by 2. What am I multiplying by? When I multiply top and bottom by the same expression, I'm multiplying by 1. I'm multiplying by 1. This is why it doesn't change when we do this. Because you're multiplying by 1, you're not changing. But
You wrote x minus x divided by x squared plus, and then in brackets x plus c. Is it x squared or is it
No.
like the numerator is x?
if we look at the denominators when we factor them, it's x bracket, I know, it's x bracket x plus 3. So all we need to do to make them the same is to multiply the second one top and bottom by x, the first one. So what I'm multiplying by is I'm multiplying by 1. So here I'm multiplying by x over x. Here I'm multiplying by x plus 3 over x plus 3.
You just have to do the same thing. Yeah. It's like making the same thing normal. Just like a normal fraction.
Alright, so now we can combine these fractions together and we're going to get 3 over x squared x plus 3. So then we have to decide what our excluded values are going to be. So our excluded values are anything that sets the original equation's denominator equal to 0. So our excluded values are going to be, we have a 0 and negative 3.
That's interesting.
Would you get around?
What will make the first fraction 0? 1 over x squared. If we set the x equal to 0, you get 1 over 0 squared, 1 over 0, excluded.
Oh, it's just how do we? So is there not a hole in this one? If they don't cancel out,
Let me just scanning it through.
But 9 times 0 is what?
If we were to sketch this as a function, you mean, there wouldn't be a hole. There's going to be a couple of asymptotes. There's going to be the horizontal asymptote of y equals 0.
how do we know this?
The
Wouldn't 1 over 0 be that?
It's from the degree of the degree of
Sorry. The function is going to have a vertical asymptote here at x equals minus 3. It's going to have a vertical asymptote here at x equals to 0. It's going to have a horizontal asymptote of y equals to 0. It's going to do this sort of here. I'm not sure whether I got this the right way or not. But it's going to look something like this. This is a more complicated one to sketch, so I'm just giving a rough sketch of it, the kind of idea, to answer your wonderings.
Yeah, but wouldn't 1 over 0 be on different?
It is, that's why there's asymptote.
Wait, how did you find the horizontal asymptote?
The degree in the denominator is greater than the degree in the numerator, which means as we approach the left hand, as we approach infinity from the left hand side and the right hand side, we will go towards 0 in both directions. Because you're dividing a constant by bigger and bigger numbers.
How did we get?
Path, can we focus on the math? Close your computer.
How did we get a horizontal asymptote at y?
I just answered that question.
Oh, I didn't understand.
The degree of the polynomial in the denominator is bigger than the degree of the polynomial in the numerator. Horizontal asymptote y equals to 0.
So when it's bigger than the numerator.
When the degree of the polynomial in the denominator is bigger than the degree of the polynomial in the numerator, we have a horizontal asymptote y equals 0. If the degrees are the same, we have a horizontal asymptote y equals a, where a is the quotient of the lead coefficients of each. If the degree in the numerator is bigger than the denominator, we get a slant or higher degree like a parabolic or a higher degree polynomial asymptote, depending on the difference in the degree. So if you're 1 degree higher in the numerator than the denominator, you'll get a slant asymptote. If you're 2 degrees higher in the numerator than the denominator, you get a parabolic asymptote, and so on. Let me not digress too far. Alright, so this is a slightly harder thing. What we're going to do here is we're looking at a process to express this as partial fractions. What we want to do is we want to split this up into separate fractions. So what we need to do with this process is we're going to start by factoring. Let's start by factoring the denominator over here like this. Are you practicing for tonight?
That's just how you
What is the, can we factor this?
I just wish I had it for you. Yeah.
Can we factor this?
Yeah. Yes, you can. 9 plus 6 after 1 is 6. I just do it. Yeah.
X plus 2, x plus 3. Okay?
Yeah.
So, if we were to have this as partial fractions, we would want it to be x plus 2, x plus 3. like this.
What did you do?
So we have to figure out what is going on top.
Negative.
We have to figure out what is going on top. And then we've got it separated into partial fractions. So the relationship here between this one and this one. So if we were to, if we look at going from here to here, if we look at going from here to here, how do we combine the two fractions? How do we combine the two fractions? We would multiply, sorry, we're looking from going from here to here as well. We're looking at going from here to here. How do we combine? We would combine with a times x plus 3. We would combine b times x plus 2. So all of this is possible. All of this is possible. So that leads us into the equation that 1 has to equal a bracket x plus 3 plus b bracket x plus 2.
So how did we get A and B?
We're getting there.
Oh.
Can we just wait?
Wait, if we're doing
Today's
cross
negative.
multiplying that in the second step, then
I
how come in the denominator there's still the x plus 2x plus 2?
So the process of combining these two fractions in the middle with the common denominator is to multiply this one top and bottom by x plus 3, creating this denominator. To create the common denominator in the second one, the process is multiplying top and bottom by x plus 2, creating the common denominator, thus creating these numerators like that.
Oh.
Okay? Are we okay with our, it's really important that we're okay with this equation now. So this denominator and the original denominator, I'm at focus. This denominator and this denominator are the same. If these denominators are the same, then these numerators have to be the same. And then we have the same expression. So now, we take this equation, I'm going to take it twice. We can put in any value of x. X will vary. It will be all values. We'll go from negative infinity to positive infinity. But we'll pick wisely. We'll pick wisely. I'm going to choose to insert x equal to minus 2. Why?
So you can cancel out.
So if I put x equal to minus 2, I'm going to get 1 bracket. So what will go in this bracket?
Minus 2. Oh, yeah, so
Minus
1.
plus 3, 1.
What is the value of a?
Should be 1.
1. A. And then
What should I choose to stick in the second time?
negative 3.
I'll stick in negative 3. So if I stick in negative 3,
Then b will be negative 1.
I'm going to get 1 is equal to b bracket. This one will cancel. What do I get here?
Negative 1.
What is the value of b?
Negative 1.
Yeah.
So, if I wish to do a partial fraction decomposition of this, I can write it as 1 over x plus 2 minus 1 over x plus 3. These have to be the same. Take a minute now and check. Combine these two together and simplify. Take the partial fraction answer on your paper. Combine the two fractions together with a common denominator and simplify. Where do you end up? Verify our answer.
Minus 1.
I'll give you a minute for that.
Okay.
Okay, so
By the one on the left.
we can verify this solution and show that these two are the same, that this is the correct partial fraction decomposition of our original expression, and we can verify it like this. All right, to finish off today, have a go at this question for yourself. I'll give you 3 minutes. 3 minutes.
This is the x squared.
Okay, so we start by factoring. If you notice here on the second one, I could cancel an x in that one, but there's no point, so I only have to put it back in again with this one. So I'm going to multiply through now and make our common denominator. So the first term, stick it inside a bracket, x squared plus 4x plus 2. We're going to multiply that by x plus 1. Our denominator is going to be x squared bracket x plus 1. So our second term here, we need to multiply top and bottom by x. So this is going to be plus x.
Why not x squared? Because you have to make it
So the first fraction, I'm multiplying top and bottom by x plus 1. The second fraction, I'm multiplying top and bottom by x. I get x squared, x plus 1. So now, I need to do an expansion of this. I need to do a distributive expansion of this. I'm going to multiply through. So x times x is going to give me x cubed. I'm going to get two x squared terms. I'm going to get an x squared term and a 4x squared term. I'm going to get two x squared terms. I'm going to get an x squared term and a 4x squared term. So this gives me 5x squared. I'm going to get two x terms. I'm going to get a 4x and a 2x. I'm going to get a 4x and a 2x.
Yeah.
So I'm going to get 6x. I'm going to get one constant at the end, which is going to be plus 2. When I combine these two together, my x cubed term will get added to this x cubed term, giving me 2x cubed.
Sir? Could you use the binomial theorem?
You don't want to.
No. No.
So what's the...
No. There's no power.
Oh, yeah, you're right.
Okay, so what I want to do now...
But Miss, I have a question, please.
Best keep it in your head. Okay. What I'm going to do now is I want to factor the numerator. I want to factor the numerator. That's a cubic. So watch carefully on this one. How can I factor? I'm going to allow use of a calculator. So in order to factor, I want to know what any of the roots are of this polynomial in the numerator, the cubic one in the numerator. So on my calculator, I'm going to use the polynomial root solver, menu, algebra, polynomial tools, polynomial root solver. I'm going to increase the degree to third degree, and then I'm going to type in the coefficients. What are the coefficients?
2, 5, 6,
2, press tab to move easily between them, 5, 6, and the last one?
2.
2. If I solve this, it tells me that I have 0, x equals negative a half. So I can turn this into a factor. What would this be as a factor?
X plus 1/2.
It could be x plus 1/2, but can I write it in a linear form?
X plus 1x minus 2.
I can write it in a linear form like this. 2x plus 1.
Oh.
Yeah, he's right. Just divide both sides by 2 and x equals 0. And then you either wait, no, so then isn't that just 0.5?
Yeah.
Isn't that just negative?
Minus a half.
Yeah.
So why don't we...
Okay, so now, how do I find the quadratic remaining?
You divide that by that. That'll take a long time.
It won't take a long time. We will use polynomial division. So I'll do a quick polynomial division. We need 2x plus 1. 2x plus 1. And then we need to divide the original polynomial by this, and it will give us the remaining quadratic.
Oh, why do we do that? Oh, no, we can't do synthetic because...
So we want to multiply by what? What do we multiply 2x by to get 2x cubed?
X squared.
So we'll get 2x cubed plus x squared. And then we do our subtraction,
4x squared.
4x squared.
So 2x.
So we're going to multiply by 2x, will give us 4x squared. And we have to drop down the 6x from here.
Yeah.
And that will give us plus 2x. We do the subtraction again.
So 4.
we get 4x plus 2. What do we multiply 2x by to get 4x?
2.
And let's just make sure that this is a solution. You can see that it is fully factorable because the remainder is 0.
So that's it.
Well, this is what we have to understand. What part of this do we want? We want this part. This is the remainder when the cubic is divided by the linear. This is the remainder.
Oh.
All right, so we've simplified. We have to also identify any excluded values. So our excluded values, what do the excluded values equal?
0.